All right, good afternoon, chemists. We'll get started with a couple announcements. So first, you might have received an email about mid-semester student evaluations, so SEIs. We're trying a new thing in chemistry and doing these mid-semesters SEIs, not just to improve our individual class, but we'll actually compare answers that you submit, the responses, I think in questions 2 and 4, across all arts and sciences to think about issues that kind of come up in arts and sciences and these large courses in general. So I'd really appreciate it if you would fill out those mid-semesters SEIs. You should have received an email about it yesterday, but you can also access it via our Canvas course, like underneath the menu items where there's like assignments, like modules and stuff. One of those is SEIs, so you can access it there as well. And you'll probably get more reminder emails. So appreciate it if you would do that. It is open until next Wednesday. All right. Yesterday, I also posted 5 practice midterms because the plan is that we'll finish chapter 5 today. And so we just have chapter 6 to get through before our midterm exam that happens after fall break. So those 5 practice midterms are already posted and the equation sheet that you will get, so you will know exactly what you'll get at that midterm. And then finally, I scheduled the midterm 2 review session, the big one. Typically, they're on Sundays because we have like Tuesday or Thursday midterms. So it's on Sunday, but unfortunately, it's like kind of on fall break, you know, like the fall break is Thursday, Friday, and so my review session will be that Sunday, but that's because our exams are just like the next couple of days there. So I did push it forward a little bit to 4 p.m. just to allow more people to come back to campus if they have plans, but also remember that, you know, it is in person here, but it's also on Zoom and I record it. So don't feel like you have to change your fall break plans to make it. So it'll just be 4 p.m. on Sunday before our exam. And it's already in our course calendar and stuff like that, so you can find that information there. All right. Okay, so that's the announcement. So let's go back to where we left off, and that was the calculation dense part of chapter 5, and that is calorimetry. So calorimetry is a method we can use to experimentally determine enthalpy of reactions. And so I have a very step-by-step process on how we do that, thinking about not only the first law of thermodynamics, but thinking about what in lab can we measure and can't we measure. So in this example, we dissolved 6.5 grams of a solid into 100 grams of water, and we saw that entire solution heat up. And so if the solution heats up, that's what we're measuring when we have our thermometer in the cup. The solution heats up, so that means the reaction had to release energy to make that happen. So that means enthalpy for that reaction is actually a negative value. It's exothermic, which is weird because we see a positive delta T. So for some reason we think, oh, Q is positive, but no. The solution, the surroundings gained energy. So that means the reaction lost energy. So that's our thought process there. We can measure the heat gained by the solution by using Q equals MCAT. Right here, where we take into the mass of the solution, specific heat of the solution, and delta T. We scale it up by dividing by the number of moles of stuff we actually reacted to get delta H. Right? So in this question, we're essentially utilizing the first law of thermodynamics. The Q lost, the negative Q lost is gained somewhere else. And so this case, we just have to very carefully define what is our system, usually it's the reaction, and then what is our surroundings. It's usually the water that's surrounding it. And so I had to skip this slide because this might help you with lab when you calibrate your calorimeter. So the idea here is when we do the first law of thermodynamics and say that the heat in the reaction is lost to only the solution, that's kind of not entirely true. So let's think about this example. If you throw a hot piece of metal into cold water, what will happen? The water will heat up. Yeah, it's going to warm up. It's going to warm up. So the idea here is that some of the heat from that hot piece of metal is going to go towards the cold water, right? But some of that heat from to warm up the cold water, but some of that heat can actually go towards the cup itself. All right, so we are just expanding the idea of what is our surroundings. So initially in the previous example, we said Q of our reaction is equal to just the Q that is gained by, the water or the solution. But we can actually expand our surroundings further by saying, oh, the reaction is going to lose some heat to the water, but it's also going to lose some heat to the cup itself. And that's what you're going to do in lab. Calculate what is the heat, heat that's absorbed by the calorimeter itself. And so the example I showed here is, okay, it's kind of like the example we did, but kind of in reverse. I give you the enthalpy of a solid, the enthalpy of dissolution of a solid, and I say that you dissolve 0.1 mole of sample. Right? So just with these two pieces of information, I can figure out how much Q is reacting, or like how much Q is coming from my reaction, from those two pieces of information. I know that that heat of reaction is going to go towards the water, and so I can calculate what is the delta T required to use up all of this energy to heat up a known amount of water, so 105 grams here. All right, so this is like a theoretical value. If all of the heat from the reaction went into the water, it should go up 5.5 degrees. But let's say that's a theoretical value. That's just using first law of thermodynamics. Everything is a perfect process. But let's say you go into lab and you actually do this. You weigh out 1/10 of a mole of stuff and you dissolve it. But let's say you actually only observe a 5-degree increase, all right, instead of 6.5 degrees. So the idea there is some of that heat in that process was actually lost by something else. All that heat didn't just go to the water itself, but it also went to the cup. So the idea here is that heat from the reaction is going to heat up the solution, but it's also gained by the cup itself, or the calorimeter. So what we do here is recognize that Q solution, we use Q equals MCAT, so we use the mass of water, specific heat of the water, delta T, and then we add this new term, the Q of our calorimeter is heat capacity of our calorimeter, and that's what you will calculate in lab. And so what we see here, we can go ahead and go through all of our known values and calculate the heat capacity of our calorimeter is about 130 joule Kelvin in this example. So for every degree increase of the water that's absorbed, the cup itself also absorbs 130 joules of energy as well, in addition to the water. So that's what that means. And so we need a positive value here because the cup is absorbing this energy. Right, so keep this in your back pocket, maybe just take a screenshot of it or something to have for lab. And in addition to lab, because your IHT lab is quite calculation heavy, I provided a nice resource here. If you go to the Chapter 5 lecture page or whatever, under supplemental resources, you'll see I posted a graphical guide to calorimetry. I go through every single calculation and defining all of the different terms, when to use what equation, and examples of each. And calculating them. So if you're having trouble with the IHT lab, I go through all the calculations here, and I think down here, here's like a real life example of calibrating your coffee cup and how to go through those calculations. Right, so if you're having trouble, do refer to that. Okay. All right, so, and the reason we're skipping this is because we will never assess this on the exam. All right, it's way too calculation heavy to assess this on the exam, but you will be doing it in lab. All right. Okay, so this question, we could assess you on the exam. This is another way to calculate delta H of a reaction, but it's just a little bit different. In the first example, we dissolved a salt and it heated up the water. This one's a little bit different, but similar in that we are mixing HCl and sodium hydroxide in a cup, and it's heating up the water again. So what kind of reaction's happening here? If we're reacting HCl and sodium hydroxide, that's called a neutralization, yes. Perfect, so we are mixing some HCl and some sodium hydroxide in a cup, and it raises the solution by that temperature. So just based upon the temperature change, can you tell me the sign of delta H? The temperature of the water is going up, so that means the reaction is endo or exothermic? Exothermic, so that means delta H must be negative. It has to be, because delta T is 6.5, I think. Okay? All right, so that's like 50% of the question right there. All right, it's just getting the sign of delta H. All right, so we want to calculate enthalpy of this reaction. Okay, so we're just going to utilize the first law of thermodynamics again. Q lost is Q gained somewhere else. And so since we're studying a reaction, it's probably best if I just say, okay, the reaction is losing energy, and it's being gained by what? The solution. Yeah, I was going to say water, but technically it's a solution, a salt solution. Yes. Okay. Our thermometer is measuring what? The reaction. When we put the thermometer in the cup, it's measuring what? The reaction or the solution? The solution. So what we're going to do is we're going to Q equals MCAT, Q solution. So Q solution, so we're using what equation? This one, right there. All right, Q solution is equal to the mass of the solution times the specific heat of the solution times the delta T of the solution. Okay, that's negative Q reaction. All right, so let's go through those values. What do we know? Do we know the mass of the solution? Is that given in the question? Yes, you mix 50 milliliters and 50 milliliters. So water has the density of 1 gram per milliliter, and I think I even tell you, assume that the final solution is that volume with this density. So the mass of our solution is 100 grams. Agreed? Okay. Do we know the specific heat of the solution? Look at the question. Yes, it is the same as water, so 4.184. And then do we know the delta T of the solution? Yes, we do. It's 6.5. Okay, so we just plug and chug at this point. So negative Q reaction equals mass of the solution, so 100 grams, times specific heat of the solution. So it's the same as water, so 4.184 joule gram degree Celsius, delta T, so 6.5 degrees Celsius. Great. So put that all together. We get negative Q of our reaction is 2,719 joules. So this means that the solution, when it got heated up, it gained 2,700 joules of energy. If the solution gained 2,700 joules of energy, where did that energy come from? The reaction. So that's where this negative sign comes into play. So if I, rearrange things to make Q reaction is actually equal to negative 2,700 joules of energy. So what that implies is that the reaction lost 27 joules of energy to thus heat the surrounding water. Okay? Because when you put the thermometer in the cup, it's not touching the individual HCl and sodium hydroxide particles. No, it's just touching all of the water that's in there. All right, is that my answer? No, I want delta H. And delta H is in a per mole value. So we need Q reaction, which we already have, but we want to divide by a mole amount. So if you look at the question, it's saying divide by the mole amount of HCl. So we just need to figure out how much HCl reacted in this reaction to figure out the enthalpy value. So like before in the sodium hydroxide example, I just figured out how much sodium hydroxide in moles did I dissolve. So in this example, we're just dividing by how many moles of HCl am I reacting. Right? And so to get the mole amount of HCl, you want the volume and the molarity. And so that's given right here in the question. So we react 50 milliliters, so 0.05 liters, with 1 molarity of HCl. So that's all of the HCl in the sources of HCl in this reaction. And so if I can do math, I can see that that is 0.05 moles of HCl that is reacting in this reaction. So what I have circled up there, that's my denominator in the delta H equation, and then the green squared one down here, that's my numerator. And so putting all of that together, Q reaction, I'm just going to convert that into kilojoules right off the bat. So negative 2.719 kilojoules. That's how much this reaction gave off, like this little amount of reaction. But to get it to a mole amount, I divide by 0.05 moles of HCl, and then you get that value that this reaction, if you were to react a mole's worth of HCl, if you neutralized a mole's worth of HCl, you would give off 54 kilojoules of energy in doing that, right? So this us dividing by moles just gets it to a per mole amount. Yeah? I'm not sure. You can look it up. You can look it up. Yeah, the question was, are the useful equations on your sheet? I mean, all of these are the same. It's negative Q equals positive Q of something else. So all of those ones are the same. It's just me trying to get you to think about where is heat going. Usually it's from reaction to solution. Q equals MCAT, and then like specific heat, using specific heat versus heat capacity. Really, the equation is in the unit itself. So, but again, just look it up because it's posted now. Okay, so there's that example. This strategy was the exact same. Track where the heat's going from the reaction to the solution. We can measure the solution, relate that to the Q of the reaction. Do not forget that negative sign. Do not forget that negative sign, because we do, in fact, get a negative delta H value at the end, and that is consistent with our observations. All right, so let's do one more. This one's a little bit different, and it's more similar to how we calibrate our cup. I think this is what you do in lab. I'm not quite sure if you do this in lab, but it's a little bit different. Okay. Because it's a reaction isn't happening, it's just a process. So here we are throwing a hot aluminum cube into cold water. And I want you to calculate what is the final temperature of the water. So let's, let me just show you what's happening here, all right? So you throw a hot piece of metal into cold water. You guys already told me that our intuition says, oh, the water heats up, right, when you do that. So some of that heat from the hot piece of metal is going to go into the water to the point where both of them are just warm. At a certain point, when we've obtained thermal equilibrium, the temperature of the hot object and the water will be the same. So the idea here is that the final temperature of the metal and the water are actually the same value, the final temperature. Right, so that's what I have here. The final temperature is the same for both of those objects, and that's what we're calculating. So it allows us to have one variable here, right? So in this example, I actually want to start it off the exact same. I always like to say, think about, okay, the heat lost by something is always gained by something else. It's just this case, it's a little bit different because it's not a reaction. So if you look at this picture, hot object into cold water, what's losing heat? The hot thing, yeah, so the metal, right? So I can rewrite negative Q loss. I can write that as Q, I'm just going to call it aluminum. The aluminum is losing heat. Where's heat being gained? The water, yeah. So Q, negative Q aluminum equals Q, positive Q water. Perfect. Okay. So now the question is, can I measure these things? Can I measure these things? So remember the different ways we can calculate Q. We can use Q equals MCAT with specific heat, or we can use Q equals heat capacity delta T. But let's see which one is more useful to us. Do we know the masses of aluminum and water? Do we know the masses of the aluminum and the water? Yes, we do. They're given. So we're probably going to use this Q equals MCAT, all right, for both of them, because we know the masses of both the aluminum and the water. Do we know the specific heats of the aluminum and the water? Yes, we do. So what we're going to do in this example is Q equals MCAT both sides. But we want to make sure that we keep the variables the same. So make sure aluminum stays with aluminum, water stays with water. All right? So we're going to use Q equals MCS delta T. Oh, this is why I call it Q equals MCAT, because M, C, and then the triangle is like an A. So it's Q equals MCAT, if you were wondering. Okay, so then I'm going to apply that to both sides of this equation. So negative mass of the aluminum times specific heat of the aluminum. And then I'm just going to rewrite delta T as T final of aluminum minus T initial of aluminum equals all the same stuff but for water. Mass of the water, specific heat of the water, T final of the water minus T initial of the water. So see, I just did Q equals MCAP for both. So if we go through all of these values, you can see we're actually just left with one variable. I know the mass of aluminum, it's 35. Specific heat of aluminum, it's given. I know the initial temperature of the aluminum. I know the mass of the water, I know the specific heat of water, and I know the initial temperature of the water. So if you look here, the variables left are the final temperature of the water and aluminum. But what's special about those two numbers? They're the same number, so I can actually just simplify it and call it T final instead. So we see we have one variable, but it just shows up in two spots, so I have to, you know, move stuff around in it, and that's annoying, but we can do it. This is an expression we can actually solve. So let's put in those actual values. Mass of aluminum, 35 grams. Aluminum specific heat is 0.88. I'm going to drop the units. T final, that's what I'm solving for, minus the initial temperature, so 95 degrees Celsius. So that's my aluminum side, equals mass of water. So mass of water is 180. Specific heat of water is 4.184. Times T final, that's what I'm solving for, minus 19 degrees Celsius. Okay, so we are just solving for that term. It just shows up into two places. I'm not really good at teaching math, but what I did is I distributed these numbers across the parentheses, and then I'll combine TF terms and the constants. Yeah, question? Do we ever have you memorize anything? I mean, other than like polyatomics. No, these values will be given to you. Yes, they will be given to you. I mean, I give it to you right here. Yeah, they'll be given to you. Okay. But not always do you have to use it. That's the thing. We might give it to you, but might not have to use it. Okay, so, but I promise you, you will use the specific heat of water so much you will probably just memorize it. Okay. So I'm going to distribute everything. And just to prove you I know how to do math, we get negative 30.8 T final minus, so I'm just distributing across that parenthesis, plus, plus 2926. I'm going to just drop the units. I know that T final needs to be in Celsius. And then on the water side, it's 753 T final minus 14,000. All right, I'm going to combine the TF terms and the constant terms. So TF is on one side, so I get 783.8 T final equals 17,000 something. And then when you divide both sides by 783.8, you get that the final temperature is something like 22 degrees Celsius. All right. Yes, so, yes, that one's a little bit more mathy because we have a variable in two different spots, but you can do it. So let's think about this answer. Let's not move on before we think about this answer. Does an answer of 22 degrees make sense? I started with something at 90 degrees, something else at 19 degrees. When you combine them, they should be somewhere in the middle, right? Because if you forget the negative sign, you'll get a weird number. You'll get something like 15 degrees. You'll get something weird like that. So hopefully if you can just take a second and think about your answer that you're submitting, like if you combine something that's 90 degrees and 19 degrees, you combine them and get something that's 10 degrees, that makes no sense. You put a hot object in cold water and it gets colder. Right? So if you observe that after you do all your calculations, hopefully you can take a second and think, oh, that doesn't make sense. Maybe, you know, I'm missing a a negative sign somewhere or messed up a sign somewhere, all right? Because putting a hot object in cold water should not make the water colder, it should make it warmer, all right? So in this case, we're still using the first law of thermodynamics. Heat lost by something is gained by something else. In this case, it's aluminum and water. We have this heat transfer, and we can Q equals MCAT both sides. We just have to be very careful about assigning those variables to the correct things. All right. Okay, so that is calorimetry. So I will point out this question, the past 3 questions we've done, very math heavy. If this question is on the exam, just skip it. I'm giving you permission to just skip it because I don't want you to spend 20 minutes on this and then still get it wrong. Okay, so just skip this question and leave it for the end. Yes, we can predict the signs and stuff, but there's a lot of places where you can go wrong in terms of your math. So I'd really like you to just skip it and get the other conceptual questions out of the way before you return to this question. So an example would be like this slide, right? These are conceptual questions. These ones you could answer in 30 seconds in theory, okay? Let's look at the second set first. All right, so I want to remind you that, the Q involved in your reaction is always gained by something else, right? The heat released in your reaction is gained by something else. So the heat of your reaction is usually gained by your water, which is typically mass of your solution, specific heat of your solution, and then there's that delta T term, all right? Okay, so here's the scenario. You dissolve 1 mole of solid to make 2 liters of solution, and you observe a 4-degree decrease in temperature. So with that information, you have Q information, how much heat is produced in this reaction given this scenario. So how do you think the temperature of the water will change if we dissolved 2 moles of solid instead in still 2 liters of solution? What do you think the temperature change will be? So how are we changing from the 2 scenarios? We're going from dissolving 1 to 2 moles. So how will that change this reaction? We're doubling the amount of stuff we're dissolving, so we're actually doubling Q, right? We doubled the size of our gas tank. If you have a gallon of gas and you can go 30 miles, how far can you go on 2 gallons of gas? 60 miles. Okay, so if we're doubling the amount of Q, what is the temperature change we're going to observe? What do we think? Anyone want to be brave? It's going to be related to 4. 8 degrees, yes, because we are doubling the amount of Q involved in this process. We've doubled our cooling power, right? Okay, so this one's a little bit trickier. 2 moles of solid dissolves in 1 liter of solution instead. 1 liter of solution. So it's still 2 moles, so we've still, compared it to what we started with, we still doubled the amount of Q involved in this process. But what's up with this 1 liter of solution, right? There's less junk that I have to heat up. So is it easier or harder to heat up 1 liter of solution versus 2 liters of solution? Easier. So if we go back to like my car example thing, so it's like I am comparing 1 gallon of gas to 2 gallons of gas, all right? So I've doubled the amount of energy output I have, but at the same time, I'm making my car smaller. I'm making my car smaller, so I'm improving fuel efficiency here. So that's what I'm doing here when I go from let's heat up 2 liters of solution to 1 liter of solution. So with those 2 things combined, what is the temperature change we're going to observe? 16 degrees, yes, very good. It's a 16-degree temperature, and it's still a decrease because this is an endothermic process. All right, so we doubled the Q, but we actually halved the mass of our solution. So if you kind of bring it back to this idea here, we'll see if we double Q, halve mass, we actually have to times 4 delta T to make everything stay equal to one another. all right, if you relate it back to this equation. Okay, so I wanted to do that one first because the last class they had trouble with this first one. So let's go back to the first one. All right, because this one's not dissolving a salt, we're doing a neutralization. So we are mixing 1 liter of HCl and 1 liter of sodium hydroxide, 1 molarity each. And it raises the temperature by 6 degrees Celsius. So what would happen if we mixed 2 molarity HCl and 2 molarity sodium hydroxide? What do we think? So think about what is the difference of those two scenarios. The only difference is concentration. What's the unit of concentration? Moles per liter. So are we reacting the same amount of moles, more moles, less moles? More moles. So how is Q changing here? It's doubling. So tell me, how is the temperature going to change? Also double, yeah. So we are doubling Q because concentration is doubling. So we will see a what increase? 12 degree, or no, I don't know how to add. 12 degree increase here. So it's a 12 degree increase because we are still heating the same amount of solution, or the same mass of solution. All right? Okay. What if I changed it to still 2 molarity sodium hydroxide, but we wanted to heat up 4 liters of solution? What would the temperature change be? It would be what? It would be 6. Yeah, it would stay the same because we double Q. We're doubling Q, the amount of heating power we have, but we're also doubling the amount of stuff we have to heat up. So we're doubling our mass. So they would cancel out, so we would double this value and double that value. So delta T would actually stay the same. It would be 6 degrees. Very good. Okay. Okay, I'm just going to skip this answer because it has to do with lab. Which one has the smaller calorimeter constant? It would be the Yeti cup. All right, the Yeti cup. Yeti cup it is smaller, so meaning that we can actually ignore the Q-cal idea here, and we can say that in a Yeti cup, if we were doing a reaction, heat transfer would be a lot more efficient in a Yeti cup because you pay, I don't know, how much is that Yeti cup? Probably like $50 or something stupid like that. You pay a lot of money to have efficient heat transfer that this object has a very small calorimeter constant, meaning it does not absorb heat from the like hot drink inside of it. That's why our liquids stay hot or cold in a Yeti cup versus like a Starbucks cup, where there's a lot of heat loss there because it has a large calorimeter constant. Okay, all right. So so that is coffee cup calorimetry. So let's move on to the last type of calorimetry, and that's bomb calorimetry, which is actually easier. All right, bomb calorimetry is easier because in bomb calorimetry, we have to give you the calorimeter constant. We have to give you the total heat capacity of the entire instrument, and that's usually given as Ccal. So let's look at the units of Ccal, heat capacity. It's joule per Celsius or kilojoule per Celsius. So is there any mass? Do I have to multiply by mass at all if I'm given heat capacity? Nope. So remember the two types of Q ways we calculate Q. It's Q equals MCAT, so Q equals MCS delta T. That's the one we've been using up until now. Then there's also Q equals capital C, so heat capacity delta T. So this is Q equals cat, I guess. Yeah. So we're using Q equals cat. We don't need any mass value, but we're typically given that heat capacity value. All right, so as long as we know what the temperature change is in a bomb calorimetry experiment, we can figure out the Q involved in that reaction. All right, so why use bomb calorimetry over coffee cup? Bomb calorimetry is used when gases are produced in the reaction. Typically, these are combustion reactions. They actually use bomb calorimetry, so like the nutritional labels on your stuff, like on your food and stuff, like a calorie. All right, a calorie actually is an energy density value, and how they calculate it is actually with bomb calorimetry to figure out how much energy is stored in those like food items that we eat. So yeah, bomb calorimetry. So how we calculate it is still the same using the first law of thermodynamics. The heat lost is always gained somewhere else. So in this case, the calorimeter is gaining heat while the reaction is losing heat. All right? But the only difference here is that Q-cal is now, we're using Q equals cat equation where we use the heat capacity instead of specific heat capacity. So do note that we have that negative sign floating around because we are utilizing the first law of thermodynamics. Right? In this case, I have it on this side. Whether it's on either side, it's still the same equation. All right, so we're just using heat capacity instead. We're still measuring the temperature change in the calorimeter. All right, and so because we're not using specific heat, we do not need the mass of the water at all in bomb calorimetry. So let's look at this example. All right, we burn some quinone, and the calorimeter has a total heat capacity of 7.8 kilojoules per degree Celsius. The calorimeter increases this temperature to that temperature. All right, that's basically all the information we need. So kind of going through the same strategy as before, use your intuition to determine the sign of delta H. Okay, so if the temperature of the calorimeter increases, is the calorimeter the system or the surroundings, you think? Surroundings, yeah, just like the cup, our coffee cup experiment, it's the surroundings. So if the calorimeter heats up, that means the reaction had to have lost energy. So what is the sign of delta H? Negative. Okay, good. All right, that's 50% of the question. So now we just need to calculate Q. Similar to how we did it before, but instead of using Q equals MCAT, we are using Q equals heat capacity instead. All right, so I'll kind of start it off how I always start it off. The heat lost by something is always gained by something else. That is the first law of thermo. So I'm going to say the heat lost by my reaction is gained by my calorimeter. Okay. And so since the total heat capacity of the calorimeter is given, I'm going to use the Q equals heat capacity equation in replace of Q cal, because I can measure that. So Q cal is equal to C cal, calorimeter, delta T. I know both of those values, and that equals the negative Q reaction. And this looks very similar to what we've done before. We can't measure Q reaction directly because my thermometer does not touch the particles, but I can measure changes in temperature of the surroundings. In this case, it's the calorimeter. All right, so going through this, the values we know, I know C cal, that's given, it's right here, C cal. And I know delta T, it's given right there, I just have to calculate it. So delta T is always final minus initial, it's positive something. 7.13 degrees. Cool, so I'm just multiplying those two numbers together in this next part. So negative Q of my reaction, my calorimeter is gaining 7.854 kilojoules per degree Celsius times delta T, so 7.13. So my calorimeter gained 55.9 kilojoules of energy, okay, because it heated up. If the calorimeter gained 55 kilojoules of energy, where did that heat come from? The reaction, yep, so negative Q reaction. All right, and now just associate the correct sign. So Q reaction is equal to negative 55.9 kilojoules. And that makes sense because this is an exothermic reaction. All right, that the exothermic reaction has to heat up the calorimeter, and that's what we observe. But is that my answer? No, I actually want the enthalpy of combustion. So I want delta H. So in order to get that, I need to divide by the mole amount that's actually present. So the way to think about it is that when I burned 2.2 samples, I got this much heat. So I just want to figure out how much heat is produced if I react a mole's worth of my of quinone here. So what I'm going to do is delta H is still the same, Q reaction over mole amount that we're actually reacting. So it's negative 55.9 kilojoules. That's what we just calculated. But I just need to convert that 2.2 grams into moles. So 2.2 grams of quinone. I even give you the molar mass. So 108 goes on the bottom, 1 mole. All right, so do the denominator first to get a mole amount of quinone, and then divide that by the Q amount that we actually calculated. And so when you do that, delta H does come out to be a negative value, negative 2,700 per mole. So what that means is that if you burn a mole's worth of quinone, it should release 2,700 kilojoules of energy. All right. This is a combustion reaction, so like intuitively you should know that this reaction needs a negative delta H value, right? So do check that, check your signs, because if you're going to mess up, that's what you'll mess up. All right. So this one definitely, it's still the same thought process, you know, check your signs, but the only difference really is this step right here. Right? Instead of using specific heat like that of water, we use the total heat capacity. And so there's a piece of distractor information in this question, actually. If you look closely, you might have seen, oh, I tell you that there's 300 milliliters of water, but because I give you total heat capacity, you don't actually need it. That the total heat capacity includes that 300 milliliters of water. All right. Okay, so that's bomb calorimetry. Follows the same steps. All right. All of these are experimental ways to determine enthalpy. I will say that they are harder and more math-consuming, time-consuming also. So let's look at the other ways I promised you that will calculate enthalpy, and these ones are much easier, right? Because they're all book values, but the thing is that they're all theoretical values, right? So we can calculate the enthalpy of any reaction by looking up table values. If we know the balanced chemical reaction, we can actually just take values for the products and the reactants and figure out the enthalpy of that total reaction. Because we're able to do that because of Hess's law and enthalpy being a state function. So how we do that is by using formation values, right? So every substance has a formation value. Formation enthalpy value. You can go to a table and look up these formation values. So we just need to define the definition of the enthalpy of formation. And so that definition is the energy involved for forming 1 mole of that substance from its elements in their most stable state. So these are some examples of elements in their most stable state. Oxygen gas, nitrogen gas, zinc solid, iron solid. So it's all of the elements, how you imagine it would look if you had a hunk of it standing in front of you, or if you just were holding a hunk of it. If you were holding a hunk of aluminum, it would just be aluminum solid, right? If you had hydrogen, it would be in the form of hydrogen gas. And so these are always going to be our reactants in a formation equation. All right, and so we want to form 1 mole of that substance. So for example, here's an example. Let's write the enthalpy of formation for methane. So note here I have methane as a product, but when you go to a table, what you'll just see is the substance methane, and you'll see like a number. You'll see that the formation value for methane is some number. I'm just going to make something up, like negative 104 kilojoules or something. But we need to infer what that value means. This enthalpy value has a reaction associated with it, and that's us writing the formation of that substance from elements in their most stable state. So our strategy here is you make methane the product. We go through all the elements and think about what are the elements in their most stable state. So the first one is carbon. So carbon in its most stable state is a solid, and specifically it's graphite. Because carbon also has another allotrope, it's diamond, but graphite is actually more stable. So you know this the saying, what's the saying? Diamonds are forever. They're actually not. It's graphite. Graphite's more stable. That you'll learn in Chem 1220, that all diamonds are spontaneously converting into graphite, but it'll take billions and billions of years. But yeah, diamonds aren't forever. Wait until chapter 12 and I'll rant more about diamonds if you want to hear about it. Okay, so that's carbon. Then the next element is hydrogen. And so hydrogen in its most stable state is what? H2 what? Gas, yes. Right? Okay, so we formed one of the product. Now we just need to balance it, making sure we still form only one product. So in this case, we're just going to put a 2 in front of hydrogen. Right? Okay. Sometimes when you balance, there's going to be fractions, and that's okay. You want to keep those fractions, because the definition of formation is we want to form 1 mole of product. All right, so let's look at another example. Okay, so again, this is what you'll look up in your book. Like you'll look up, okay, the enthalpy of formation of ethanol. Right there is ethanol, is that value. Right, delta H of formation is negative 277. So that number has a reaction associated with it, but it's not written. We have to think about what it is, right? Like what is implied for that reaction. So again, let's write that balanced equation for ethanol. Ethanol has to be the product. So C2H5OH liquid. So basically, I'm asking you, what is the reaction associated with this negative 277 kilojoule value? All right? And so this is us writing the reactants and the reactants of the elements in their most stable state. So we just go through all the substances again. It's carbon again. So this is my graphite. We have hydrogen gas again. What is oxygen in its most stable state? O2 gas, very good. All right, those are my substances. We just now need to balance it. So again, ethanol, the thing that you're making, that has to keep a 1 coefficient. So we want to have fractions in the reactants if needed. So we're going to put a 2 in front of carbon. What's the coefficient in front of hydrogen? What is it? 3? Yeah, because there's a total of 6 hydrogens on my product. And then the coefficient in front of oxygen? 1/2. And we're going to keep that fraction, right? Because again, the definition of formation is forming 1 mole of product. We don't want to multiply everything by 2. We don't want to do that. Because if we do, then it's no longer a formation value. All right, because then we'd be forming 2 ethanols. We don't want to do that. All right. So yeah, when you look up these formation values, this reaction is what's happening to make that value. Okay, so let's do some more. So let's write the reaction, the formations of these reactions. So the strategy is that these are going to be your products, and we need to just go through and make sure we appropriately assign and balance those reactants. So Na2CO3 is my product. So I have some sodium. What's sodium in its most stable state? It's a solid, yep, because it's a metal, just like aluminum or tin or lead or something. Then we have carbon. This is graphite again. Solid graphite. And then we have oxygen, and we already said this is O2 gas. Okay, so now we just need coefficients. It looks like I need 2 sodiums, 1 carbon. How many oxygens? 3/2. Yep, and then that's it. Do not try to get rid of fractions. Keep them there. All right, so if you look up the value for sodium carbonate, it'll give you a value. This is the reaction it's referring to. All right, let's do the next one, this silicon bromide thing. So we got silicon, 3 hydrogens, and a bromine. It's a gas. That's my product. So let's go through the elements. These ones are a little bit trickier. What do we think silicon is? Look at the things around it. Maybe that'll help you. Yeah, it's going to be a solid. Silicon is in the same group as carbon. Since we said carbon was a solid, silicon is probably also going to be a solid. All right, then hydrogen, we know that one's H2 gas. And then what about bromine? Br2, but it's a liquid. Yeah, that's the weird one. That's why I included that one. So bromine is a diatomic, but it's not a gas at room temperature, it's a liquid. All right, then we just need to appropriately balance it. So in front of silicon, a 1, in front of hydrogen, 3/2, and then in front of bromine, a 1/2. Good? All right, let's do the last one. O2 gas, so same strategy. O2 is my product. How do I form O2 from elements in its most stable state? It's the same, O2 gas. Great, that's it. Why did I include that one? So, for fun, do we know the values of any of these reactions already? Technically, we do. So these two, sodium carbonate, the silicon bromide one, we'd have to look those ones up. But technically, you should already know what the formation value of this last one is. Just use your intuition. How much energy does it take to go from O2 gas to O2 gas? 0, because we're already there. Yeah, okay? And so I think I wrote it here. Any element that's already in its most stable state, so O2, has a formation value of 0. So if you go to a table and try to look up the formation value of H2 gas or graphite or oxygen gas, either you won't find a number or it'll just say 0. And this is why. Because if you try to write the formation reaction for forming O2 from elements in its most stable state, you see that there's no reaction at all. So that's why delta H is 0 for elements that are already in its most standard state. So do keep that in mind, because you might run into a question where it looks like they don't give you all the information you need, but they did. It's just some of the values are 0. You just need to, use your intuition a little bit, chemical intuition, to figure out which ones are 0. All right, so how is this helpful for us? We can use delta H of formation values, things we can look up in a table to calculate the delta H of a total reaction. All right? Okay, so if we take into account all of the formation values of our products, all of the formation values of our reactants, subtract them from one another, we can get the full delta enthalpy of a total reaction, just from formation values. The things to look out for are states, so make sure, you look at the reaction. This is water liquid. Make sure you use the liquid water enthalpy value, because see how water gas is slightly different, so you don't want to use this one, you want to use the liquid one, what it says in the reaction here. And we also want to pay attention to coefficients. Those need to propagate when we sum up our formation values. So what I like to do is just take inventory of everything. I like to write formation values underneath the substances and add up products and reactants separately, then add them together. Because what you're going to notice is there's going to be a lot of negative signs floating around, and you don't want to mess those up. So I like to do things in separate steps. So on the reactant side, CH4 is negative 74.8. All of this is in kilojoules per mole. CO2 is negative 393.5. And water, we're going to use this value, not the second one, is negative 285.8, but there's 2 of them. So we need to make sure that we include both of them in that calculation. All right? There's 2 of them because that's in the balanced chemical equation. Where's oxygen? I didn't give it to you, so we can't do the question? It's 0, yes. So don't let that mess with you. And then 2, since there's 2 oxygens, there's 2 zeros, but it's still just 0. So at this point, I've inventoried everything. Now I sum up each side separately. So the sum of delta H's on my reactant side is negative 74.8. But on my product side is a little bit more intense. So I'm adding these 2 numbers together. What is it? Negative 965.1. 965.1. All right, so that's the sum of the reactants and the products, but when we calculate delta H of the reaction, we want to take the sum of the delta H of formations. It needs to be products minus reactants. All right, products minus reactants. So once I've gotten the two sums, I will do products minus reactants, so negative 965.1 minus negative 74.8. All right, and so minusing a negative turns it into a positive, and so there's a lot of negative positives floating around. So that's why I like to split up these two steps, all right, because I don't like to distribute negatives in a bunch of places. Right, and so then, yeah, you add that up and you get that the total reaction has a enthalpy change, an energy release of 890 kilojoules of energy. So let's think, does this sign of delta H of this reaction make sense? If we have negative 800 kilojoules, that implies this reaction is what kind of reaction? Exothermic. What kind of reaction are we studying? A combustion reaction. So does it make sense? Yes, yeah, so hopefully if you do the math and you get like a positive value and you look at the reaction, it's combustion, hopefully you can recognize, ooh, I probably did something wrong, all right? Okay, this is the same delta H we've been studying for the past day. Okay, so pay attention to states and coefficients, all right? Don't use the gas one because that's not what's in this reaction, and also pay attention to states, or coefficients, all right? This is the same type of question. We're doing products minus reactants. I'm just giving you a different piece of information. This time I give you delta H of the reaction, but I'm asking you, let's calculate the formation of one of the missing pieces instead. Right? I start this off the exact same way. I like to inventory all my delta H formations. So I see that this guy is negative 84. HF is negative 272.6. We're not given this one, C2H5F, so I'm just going to call that X. That's my variable that I'm solving for. All right, so where's fluorine? It's 0, yes. It's 0. And I do it the same way. I'm going to sum up the reactants and the products, and then do products minus reactants equal this delta H of reaction, all right? So, so my reactant side, the sum is negative 84. This is reactants. Then my products is X minus 272.6. That's my products. So we just need to be careful here. Delta H of my reaction is products minus reactants. Everything's a 1-to-1 ratio coefficient, so that's nice. And so I already give you delta H of reaction, so negative 469.3. I'm going to drop the kilojoule. Everything's in kilojoules. So products minus reactants. So X minus 272.6 minus the reactants, so negative 84. And again, we're subtracting a negative, which is annoying. And so putting that together, negative 469.3 equals X minus 188.6. And so if you add 188.6 to both sides, you get X is equal to negative 280.7 kilojoules. And so this is the delta H of formation of C2H5F, that missing piece that we had. All right, so same exact thing, it's just I gave you a different piece of information. All right, do make sure to keep in mind states and coefficients if they're there, but everything in this example is a nice 1-to-1 ratio. Okay. Okay, good. Products minus reactants. So that's the second to last way we can calculate enthalpy. I would say this is one of the easier ways because it's just table values. You take it from the table values, use coefficients as necessary, products minus reactants. So the last way to calculate delta H is, again, we're utilizing the idea that enthalpy is a state function. We need to know where do we start and where do we end. But we're going to do this a little bit differently. We're going to think about a chemical reaction as like playing with Legos. All right, we have our reactants, like our little Lego pieces as reactants. We're going to break everything apart into building blocks, and then form our products. All right, so there's energy involved with breaking everything apart, and there's energy involved when we put everything back together. So we're going to be inspecting those two steps, breaking everything apart, putting things back together. So let's go back to the idea of potential energy. So remember, earlier in this chapter, we talked about potential energy. Breaking a chemical bond always, 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 always requires energy. Always. So if it requires energy, what is the sign of energy? Positive or negative? If it requires energy. Positive, yes, okay. Making a bond, so bringing two atoms together, always releases energy. So what's the sign of delta H there? Negative. Always, 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 always. Always. Okay, cool. So let's look at these examples without doing much calculations. So remember that. Okay, so A, we're turning NO2 into N2O4. Don't look at me, look at the thing. Look at the thing. So ask yourself, am I breaking bonds or am I forming bonds? And then that should tell you what the sign of delta H is. You're turning two things into one thing. So what are you doing? Are you breaking it or are you forming it? You're forming it. So what's the sign of delta H? Negative, yeah. So you are making a bond. So delta H is negative. Cool. The next one, we're taking two fluorine atoms and we're making a fluorine molecule. So what are we doing? Are we breaking or are we making? Making a bond. So delta H is negative again. Okay, great. Next one, we're taking magnesium cations and chlorine anions and we're bringing them together. Making again, yeah, so we're bringing attracted particles together. That's a decrease in potential energy. That's why delta H is negative again. So this is making. Okay, whether it be a covalent bond or an ionic bond, it's still, we're making a bond regardless of what kind it is. It is a negative, it's an exothermic process here, right, when we make bonds. Okay, last one. HBr to that one, what is it? Positive or negative? Positive, yep, because we are breaking it. We're taking one, like hydrogen, hydrobromic acid, and we're breaking it apart into two. So here we are breaking. So this has a positive delta H. Great. Okay, so we, just based upon us identifying, okay, are we making or are we breaking, we can identify the sign. So now let's look at magnitudes over here. So here's a table, and you will be given these for average bond enthalpies for different types of bonds. So here, if you compare a carbon-oxygen single bond versus a carbon-oxygen double bond, here are the bond strengths. So all of these are positive values. So does that mean these values are the energy to break a bond or to make a bond? If they're positive. Breaking, yes, this is the energy required to break these bonds. So that's sign. So based upon magnitude, if we look at the magnitude of these delta H's, okay, usually what's implied in these numbers is that if we have a strong bond, typically delta H is a fairly large number. If we have a short bond, we'll also see a large delta H value, right? So short and strong bonds have large delta H value. So you can see here, CO versus CO single bond versus double bond, we see over a doubling of the energy to break it, all right? Because the bond gets stronger and it gets shorter. Okay, all right, so all of these are energies to break bonds. So if it requires 155 kilojoules to break a mole's worth of fluorine-fluorine bonds, what do you think the energy is associated with forming fluorine-fluorine bonds? Do I have to look up another table? No, it's going to be the same value, but we change the sign. Yeah, so we can use this table for both. When a bond is formed instead of broken, it's the same value. It's just we need to recognize it's a negative energy because making bonds always releases energy. Same table. Okay. Breaking, positive, making, negative. Okay. This is my favorite way to calculate bond enthalpies because we get to destroy stuff, right? we inspect a reaction and think about them like Lego pieces. What bonds do I have to break off? And what new bonds do I make? And if I look at those table values, I can take inventory. Okay, breaking bonds is this positive energy value. Making these bonds is some negative value. Then if I add those two steps together, that's the overall delta H of my reaction. Okay, this one's my favorite. Okay, so yeah, we can imagine a reaction happening in two theoretical steps. Reactions actually don't happen this way. We want to give enough energy to break bonds, and then we form bonds. So this is a positive delta H value, and then we have a negative delta H value, and then we just combine those two steps together. All right? So here's an example. We are reacting methane with chlorine. All right, and the total reaction, I'm reacting methane and chlorine, and then here are my new products, HCl and then chloroform. So if you kind of look closely, what we're really doing is just like swapping these two atoms with one another. All right, in this reaction, we're just swapping them. But in order to swap them, what I need to do is break these two bonds. And that requires some amount of energy. So we break a carbon-hydrogen bond. We break a chlorine-chlorine bond. Now we have these like free-floating Lego pieces that we can now attach to different points. Then we want to think, okay, what bonds do I form once I broke those? So the bonds that I form are this new carbon-chlorine bond and this new carbon, or chlorine-hydrogen bond. All right, so we broke these pink bonds. We broke these pink bonds, but we made these red bonds, right? So making bonds is always exothermic, that it's a negative value. So see why there's a downward arrow here. So this is how I go about questions like this. I take inventory. I think about, okay, what bonds do I need to break? What bonds do I need to make? So the bonds that I break typically come from the reactant side, and I just take inventory of them. So we broke a carbon-hydrogen bond and a chlorine-chlorine bond. So I will just write, okay, carbon-hydrogen, and then what is this one? Chlorine-chlorine. And so those have values that I will look up. Okay, these come from the reactants. Then we make bonds to form our products. And so if you look closely, we formed a carbon-chlorine and a hydrogen-chlorine. So what we made is carbon-chlorine, hydrogen-chlorine. So now we just need to look at the table and associate those correct numbers. So carbon-hydrogen is 413, chlorine-chlorine is 242. So if you add those two numbers, it costs me 655 kilojoules of energy to break those two bonds. All right, so that's breaking. That's positive. Now I take those free, loose Lego pieces and I form new bonds, and that's the carbon-chlorine and hydrogen-chlorine. And so let's look up those numbers. So hydrogen-chlorine is 431, carbon-chlorine is 328. And so forming these bonds is 759 kilojoules. But we made these bonds. So is it positive 759? No, since we made these, it's a negative value. It's an exothermic value. So if you just want an equation to help you calculate this, delta H when we use bond enthalpies is bonds that we break minus bonds that we make, where the exothermic term is in that minus sign. So we don't have to like doubly minus it. So if we calculate all of this, we're breaking 655 worth of bonds, but then we are making 759 kilojoules. That negative sign applies the exothermic value. And so we get that this overall reaction gives off 100 kilojoules of energy. It's break minus make. Yes? So at this point, since we have, so the question is, how do we know if it's double bonded or not? You don't, because we have not learned Lewis structures yet. So if a question like this were to come on, we have to give you the Lewis structures, like in the next examples. So in this one, I give you the structures so you can clearly see what has to be made and broken. And in the next example as well, we have the structures. Good? Okay. All right, it's break minus make. But here's the thing, what side of the reaction do you break? The reactants. Yeah, and then what side of the reaction did you make? Products. So isn't it kind of like reactants minus products? So see how that's different than when we did formation values? Formations are, it's always products minus reactants. But because we're just thinking about the energies here, breaking reactants is a positive value. Making bonds in the product side is a negative value. So it's break, I like to say break minus make. But technically, you're breaking reactants and making products. So do recognize that there's a slight difference there for the last two kinds of reactions we're doing. Okay, 10 minutes. So let's do this last slide. So let's calculate the delta H for this entire reaction. So this one's a little bit more complex, a lot more going on. So here's a tip. We can just break everything and make everything. In this example, see how I didn't break the CH bonds in the methane? Because they show up over here and over here, right? Like I don't have to break and make those bonds to calculate delta H for this entire reaction. I can just ignore them. That I don't have to break apart my entire Lego castle to like rebuild it. But in this example, because it's a lot more complex, it's going to be more useful to us if we just make and break everything. All right, so we're just going to destroy everything. But the strategy is still the same. We're going to break stuff. Let's take inventory of it. We're going to make stuff, take inventory of it. But we just got to be careful about coefficients. Because I balanced this for you. We're combusting ethane. But how many moles of ethane are we combusting? 2. But then how many pictures do I have here? 1. So if we only, so in this picture, there's only one carbon-carbon bond, but in the whole reaction, how many carbon-carbon bonds are there? 2, yes. How many carbon-hydrogen bonds are we breaking? Not 6, but 12, yes, because there's 2 molecules present there. All right? So if you look closely, there are 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds on one ethane, but there's 2 ethanes there. Okay. All right, and then how many oxygen double bonds am I breaking? Careful. 7, yes, not 1, there's 7 of them. Yes. And so here's an example, see the double bonds there, so you know that this is a double bond. Okay, so that's breaking, let's do making. Here are the structures. So I'm not going to give you any hints. How many CO double bonds are there? Are we breaking? 8. Oh, you guys are so good. Yes. So you might think, oh, but there's only 4 CO2s. But each CO2 has how many CO double bonds? 2. So there's 8 COs. And then in water, how many oxygen hydrogen bonds are there? 12, because each oxygen hydrogen, there's 2 of them in a water, but there's 6 waters. Cool. All right. So that's our inventory. Now just take the appropriate numbers. All right. So 2 carbon-carbons, what is that? 348. 12 carbon hydrogens, 413. 7 oxygen, where is that? 495. Right, add that up, and we get that it requires 9,000 kilojoules of energy to break all of that stuff, to just destroy all those bonds. All right, now we take inventory of the bonds that we made. So 8 COs, double bonds, so 8 times 799, plus 12 times OH is 463. So add all those up, and there is 11,948 kilojoules. But since we're making these bonds, that's an exothermic process. Okay, so with those two numbers, what's the delta H equation we do? We do a delta H equals break minus make. Break because that's an endothermic process, minus make because making bonds are exothermic. So where am I going to write this? Okay, I'll just write up here. Okay, delta H of my reaction is break minus make. So it is 9,000 kilojoules minus 11,000 kilojoules of energy. So we get that this total reaction, its delta H is something like negative 2,831 kilojoules of energy. All right, so this is a negative delta H value, so it implies that the reaction is exothermic. Does that make sense in the context of this question? What are we doing? Combusting something? Yes, so it should be negative. All right, so we're satisfied with that negative delta H value, but let's take it a little bit further. Why is this enthalpy of reaction a negative value? Why is it exothermic? Is it because we broke bonds in ethane? So it's in the corner here. Okay, so which statement, A or B, describes why, explains why this reaction is exothermic? Is it because we broke bonds in ethane? Or is it because we formed bonds in products that are stronger than the bonds in the reactants? Which one is it, A or B? B, yes. I mean, technically A is true. We're breaking bonds in ethane, but does that explain why it's exothermic? No, because breaking is what? Endothermic. Okay, so we are done with this chapter, but I'm going to spend the minute that I have left to bash on biologists. Who has heard, all right, that in biology, when you break an ATP, you get energy? Yeah? Does that sound right? Well, it's wrong. Okay? It's an oversimplification, and it violates the first law of thermodynamics. It's an oversimplification, okay? So, like, who's heard, like, energy is stored in chemical bonds? You break bonds, you get energy. Doesn't that go 100% against what we just talked about today? Breaking is always endothermic, but making bonds is always exothermic. All right, so it was very easy for me to look up incorrect slides. All right, like I found this slide. It says ATP releases energy by breaking this bond. So Mrs. Smith says that you break this phosphate bond, you get energy for free. That goes against what we talked about today. All right? So the real way to actually think about it, remember, breaking bonds always requires energy. We think about the bonds we break, where the energy comes from. The negativeness of an exothermic reaction is actually in the bonds that we form. The bonds we form in the products are much stronger. They're at a more stable state. So it's this downward hill, all right, where we're forming stronger bonds. That's where the exothermic, that's where the energy comes from. It's not the breaking part that gives us the energy, it's the making part of the products, which in this case is ADP, so adenosine diphosphate, and a free phosphate. So those products have much, much stronger bonds than adenosine triphosphate. So moral of the story, it's the breaking does not give us the energy. It's the making that gives us the energy. But yes, the process is started off by initially breaking ATP at first, but it's, again, the way we say and the way that we teach it oftentimes implies that the breaking is what gives us the energy, but it's not. It's the making. Okay, so I'll get off my soapbox. So we're done with chapter 5. Homework is due on Monday. We'll start chapter 6. Okay.